what we're looking at here is a really simplistic representation of an atom. It is definitely not to scale, not even close to it. But what we have got is a nucleus, the first energy level, so where the the 1s orbital is, so where we'd find the lowest energy electrons if it had any there. Got the second energy level, so where the 2s and the 2p orbitals would have their electrons in 99% of the time, and those electrons have got a bit more energy, which is why they're further away from the nucleus. Third energy level, so where the 3s, 3p and 3d orbitals are, well, the 3d's more around here. Fourth energy level, fifth, and so on. Okay, so we used to call those electron shells. We used to draw electrons in pairs going around the edge of it, and that was a good representation. So that was what we called the Bohr model of the atom, and it was pretty good. Now we know it in a bit more detail, we can start to use this to explain some properties. And the key properties that we're going to be looking at are atomic radius, ionic radius, electronegativity, which we met last year, and a thing called first ionization energy. For those doing scholarship, you also need to understand second ionization energy, third ionization energy, and fourth. But I'll leave that for when you do those tutorials with Mr. French. But these are the things we need to be able to identify trends on the periodic table and then use what I'm about to talk about to explain. Okay. Ultimately, you can guess what the first two are. The radius of an atom, the radius of its ion, and that's what I'm going to base what we're going to do now on. So, as we've always been taught, and I'm not going to change the rules on you here, you have a nucleus at the centre. This should be tiny. It's very small volume, but very, very massive. It's where we find most of the mass of the atom. And its mass is made up of protons, which are positively charged, and neutrons, which have got no charge, and sort of act like the glue holding it in place. It's a bit more to it than that, but that's all you need to know for this year. Okay? So we've got not just its mass in here, but you've also got all of its positive charge found in one small place. So that positive charge is going to have an effect on anything that is negatively charged. And what we've got is we've got negatively charged areas around it. These are our electron clouds. Okay, they are of different energy levels. It gets higher the further we go out. The more protons I've got in here, the more positive charge I have on each electron. So what's that going to do to each electron? Think of it like magnets and how far apart they can be before they start jamming towards each other. If I've got a really big nuclear charge, lots and lots of protons, what's that going to do to these electrons? They're going to be more attracted. So what's that going to do if I've got an electric pull that is stronger? What's it going to do to how far away they are? Good, it's going to bring it closer together. They're still going to have the same amount of energy, okay? But they actually get pulled a lot closer. Okay, so this becomes a lot closer if the nuclear charge is bigger. And that sort of makes sense, doesn't it? So therefore, we'd expect atomic radius to decrease as we get more and more protons in here. So you'd expect them to keep getting smaller and smaller and smaller and smaller. But that's not quite what happens. It does as we go across a period, because you're not adding to the what we call effective nuclear charge. We are adding to the effective nuclear charge. We're not adding more energy levels. Okay, so first period only has electrons in this energy level. Second only has them in this energy level and this energy level. So bigger nuclear charge does pull them closer and closer together, which is common sense. However, as I add more energy levels, because the valence electrons or outermost electrons are not able to fit into these lower levels, I naturally increase the radius, don't I? It may only be a model and not to scale model, but we can see that once I've filled the first energy level, oh look, the second energy level ones are further away. And this is because they have a higher energy, so they must go in orbitals that are further out from the nucleus. So they have to go there. But as well as that, what we have is a decrease in the effective nuclear charge. And the reason is that this electron cloud here prevents some of this positive charge getting through. It's like putting a piece of paper in the way of a magnet. It doesn't stop all the magnetic attraction, but it will stop some of it. Or a different way to think of it is your desk. You could have magnet on top of the desk, magnet on the bottom, and you'd be able to move the magnet on the top because the magnetic field can go through the desk. But if I move the magnet that's underneath too far away, the effect of that magnet is reduced by the desk. This electron energy level, the electrons in it, decrease the effect of the nuclear charge on these ones. So if this is full and this is full, you can imagine how much of a shielding effect there is on these outer ones for the third energy level, fourth energy level, and so on. So what you end up seeing is that although you have an increased nuclear charge as we go down in our groups, so hydrogen to lithium to sodium to potassium and so on, for example, the radius is getting bigger, not just because the valence electrons are at a higher energy level, which is going to be at a larger distance from the nucleus. The effect of the nuclear charge is being decreased because of the shielding of the lower energy levels. Okay, so we need to consider both of these things at once. The nuclear charge is important, but then what we also need to consider is the shielding. The other thing we have to consider is the fact that you're trying to cram more electrons into a smaller space. Okay, on an atomic scale, this is a huge space because the nucleus is so tiny, but actually still trying to cram all these negative things near each other. So they're going to repel each other in these energy levels. So you have got a little bit of electric repulsion happening. The nice thing is because of the shapes of the orbits, the orbitals, that kind of is accounted for already. But it's not if we were to become, say, a negative ion. If we were to add an electron, and let's use fluorine and fluoride as an example, fluorine is 1s2, 2s2, 2p5, so 9 electrons with 9 protons. If I add another electron out here, I should make it more stable, so I should make it closer to the nucleus. That would make sense. It's more stable, so it should be able to orbit closer to the nucleus, less repulsion. It's not quite what happens. Because each electron is only experiencing the equivalent of 9 protons of attraction, minus the shielding of these ones, then when I add another one in there, what has a bigger impact is the fact that I've tried to cram 8 electrons into that energy level rather than just 7. So what happens is I go from a radius like this for the fluorine atom out to a much bigger one for the fluoride atom because I've got more electric repulsion. The last thing that we have to consider is Hund's rule. That doesn't affect atomic radius, but it can affect things like ionization energy, which you'll learn about later on, where the relative stability of different orbitals will make it harder or easier to remove electrons. And it's from ionization energy that we've been, and using Hund's rule, that we've been able to infer exactly what the electron configurations are of some of our atoms. Okay, so these are the different properties you have to justify. You have to justify it in terms of effective nuclear charge, which means how many protons in the nucleus, and how many electrons and how many electron energy levels we've got, so that you can talk about electric propulsion of electrons in the same energy level. So you can talk about shielding from electrons at a lower energy level. And so when we get to these last couple, you can start using Hund's rule to try to understand why you get some things that appear to be anomalies, strange results, particularly as I say in these two here.